We just finished talking about and probabilities. That concludes all the types of compound probabilities we need to discuss. Or probabilities, where you add the probabilities. Conditional probabilities, where the probability changes based on another event. And probabilities, where you take the two probabilities and you multiply them together. With the or probabilities, we had to talk about mutually exclusive events, meaning two events that could not happen at the same time, because that affected the results of our or probabilities. Well, likewise, there are independent events that will affect the calculation of our and probabilities. So let's talk about independent events. We've talked about conditional probabilities and use that equation to derive our equation for and probabilities. So just as a reminder, there are the equations for conditional and probabilities. Now, let's look at these two events here. First, what's the probability of drawing a jack in the second of two cards with replacement? Meaning you draw a card, you've got it, you put it back, draw a second card. What's the probability that the second card is going to be a jack? Well, what's the probability of drawing a jack? There are four cards in the deck. Four jacks in the deck of 52 cards. Whereas if you take out a card, put it back, and then pull out another card, what's the probability of that second card being a jack? It's going to be 4 out of 52. Why? Since I put that first card back, I still have 52 cards in the deck. My probability has not changed. So basically, this is saying that drawing a jack, I don't care what happened with the first card. It could have been a queen. It could have been an ace. It could have been another jack. It doesn't matter what the other first card was. Since I put it back, the probability of drawing a jack for that second card has not changed. That means that the two events are completely independent. But what if I take out that first card and I put it to the side, and then I draw a second card? Now, in this case, I start off with 52 cards, but since I pulled one out and set it to the side, now I only have 51 left. So what's the probability of drawing a jack, given that the first card was whatever, a queen, and I put it to the side? That has changed my probability. And now it's only 4 out of 51. All right. So on the left, you have an example of independent events where the second draw doesn't even care what the first one did. The probability doesn't change. But on the right, you have two dependent events, meaning the second draw does depend on what happened with that first draw. So two events are said to be independent if the probability of one event is unchanged when the other event occurs. All right. So easiest way to find out if two events are independent are looking at these two probabilities. What's the probability of A given B? If that is the same as probability of A, whether B happened or not, then they are independent. In other words, this event B had zero influence on the probability of A. Okay, B happened, but B might as well not have happened. It could have happened, it could have not, doesn't matter. The probability of A is still probability of A. It's unchanged. Let me give you a couple of examples to show what this means. Here's one example. You have 75% of students buy a hamburger. 40% of students buy ice cream. 25% of students buy both a hamburger and ice cream. Are buying hamburgers and ice cream independent? Well, let's find the probability of buying an ice cream given that we've already got a hamburger. Okay, we've gone through this process before, so let me just outline this here. What's the probability of buying ice cream if I know that I already got a hamburger? will be the probability of a hamburger and ice cream divided by the probability of buying a hamburger. Well, the probability of buying a hamburger and ice cream, that's given here. That's 25%. Probability of buying a hamburger is 75%. That comes out to 33.3%. Is that the same as the probability of just buying ice cream? It is not, because 40% of students buy ice cream. 33.3% of students who got a hamburger also got ice cream. Okay, so those two are different. Therefore, buying ice cream is dependent on buying a hamburger. Now, by that, all I mean is that buying a hamburger influences whether you buy ice cream or not. That's really all it's saying. There is an influence between buying a hamburger and buying ice cream. Now, here's another example. A student goes to the movies. 70% of students who go to the movies like to see action movies. 60% of students who go to the movies also buy popcorn. 42% of students who go both see action movies and buy popcorn. So are seeing action movies and buying popcorn independent? Let's look at the probability of buying popcorn given that they're seeing action movies. Okay, let's follow the equation. Probability of buying popcorn given that they're seeing action movies would be, what's the probability that they buy popcorn and see action movies divided by the probability of seeing action movies. Okay, probability of popcorn and action movies is 42%. And the probability of watching an action movie is 70%. That gives us 60%. Well, what's the probability of buying popcorn? It's 60%. These two give us the exact same result. Therefore, according to this example, buying popcorn and seeing action movies are independent. And that kind of makes sense, right? You go to the movies, you're going to watch your movie, you're going to buy popcorn. It doesn't matter what movie you're going to watch. That's totally irrelevant. You're going to go buy popcorn, at least. Those who like to buy popcorn are going to buy popcorn regardless of the movie. So the type of movie they go to see is not necessarily influencing whether they buy popcorn or not. There's an example of two independent events. And with that, we have learned all we need to about compound probability. Next lesson, we're going to talk about some of the rules in probability and some tools that we can use when we get back into statistics in lesson 12.